Okay, so we're doing your ophthalmic optics problem set number 2. Okay, it's entitled edge and center thickness, but it also has some, lensometry problems to begin with. So we're going to start off with those there. All right. So the first question says you're neutralizing a single vision lens with your manual lensometer, and the single lines come into focus first, and you note the power of the wheel to read +4 and the axis wheel to read 167. The triple lines come in to focus next with a power of +3/4. What's the Rx of the lens? Okay, easy enough. Now, something to understand that what you call a manual lensometer is actually a phosiometer. All right, now what does that mean? So a lensometer is the same idea as, let's say you ask someone for facial tissue, and you, instead of saying facial tissue, you ask them for Kleenex. Or you want a cotton tip applicator, but you ask for a Q-tip. Okay, and so the Reichert company is still a manufacturer of phosiometers, and they created a phosiometer they called the lensometer. Okay, and so that's where the word lensometry and lensometer comes from. But technically it is a phosiometer. Now, why do I say that? Because what it does is actually meter the focal lengths of lenses. Okay, it doesn't really measure lenses, it measures the focal lengths of lenses. How does it do that? All right, well, it's just basically two lenses. All right, in the machine, here's two lenses. All right, and it has a light bulb behind it over here. This gives off your light. All right, and right in front of this one lens is a screen. Okay, there's a screen right here, and on that screen is a set of Myers, and the Myers kind of look something like this. Okay, kind of like a cross. All right, and so it projects this phosiometer when if you set the focal lengths of these two lenses coincident upon each other, what's going to leave is parallel light coming out. In other words, this image of this reticule or these Myers is going to be clear to you. All right. When you place another lens in front of this system, all right, over here, this is going to be the lens from your glasses, let's say. All right, so this guy here is going to be the lens that you are trying to quote-unquote neutralize. All right. That is going to create this image to be out of focus. And then what you're doing is you're adjusting the distance between these two lenses and coming to a new focal point. So a focal point of this combined system here. And judging by that change in distance, the way you change the distance in the machine, there's a dial on the side. They call that the power drum. And when you turn that dial one way or the other, you're actually shortening the distance between the two, or you're spreading the distance out. All right, and that distance is converted into a dioptric value, and that's the dioptric values that you see on the power drum. All right. On this screen over here, you can actually turn this screen also. That also rotates. Okay, and that's the one where you can actually have the numbers that indicate the axis in case that you have an astigmatic lens. And so this is known as the power drum, and this is known as the axis wheel. Okay. Now, when you're talking about these the Myers over here, it's kind of strange. There's one's called the triple line and one's called the single lines. Actually, both of them have 3 lines into them, but one is significantly closer together. All right, so these are 3 lines that are much closer, and that these are 3 lines that are much farther apart. Okay, and so the ones that are closer together, they call that the single line, which is the wording that you used in your lab class, and the ones that are farther apart, you call that the triple line. Okay. All right, bear in mind that they're both 3 lines. If that didn't make any sense to you, that's why. That's just the wording that all comes in. If you put a lens in front of here, in other words, if you have no lens in there, you would dial in until these Myers actually come into focus for you, and this power drum would read 0. Okay, it's a spherical lens, then it doesn't matter where this axis wheel is spun. You can spin it all the way around. Okay, if there is an astigmatic lens, all right, instead of having both of these Meyers in focus at the same point, only one of the Meyers will come into focus, and then you would have to readjust the power wheel to have the second one come into focus. If you bring the single line in focus first, the 3 lines that are really close together, what you have found is the meridian that has the highest power. Okay. If you bring the triple lines into focus first, the ones with the 3 lines that are farther apart, that will give you the meridian with the lowest power. Okay, easy enough. You would bring those Meyers into focus, doesn't matter whether it's the lowest or the highest. You would bring that into aligned, all right, within the Meyers themselves, and that'll give you the axis. Okay. If you bring the highest power first and then readjust for the lowest power, your second number is going to be less than your first, which means that you will now have a prescription in minus cylinder form. Right? If you start out with the lowest power, and then you have to adjust your power wheel in the opposite direction to get the next one to come into focus, that number will now be greater than the first number. Right? When the difference between the two, that is the definition of astigmatism, you have now found positive cylinder. All right, so the machine, there is no minus cylinder phosiometer, there is no positive cylinder phosiometer. You can do it either way, depending on how you run. Now, being you're in optometry school, we tend to write things in minus cylinder, and so you're taught to bring the single line in first, so the 3 lines that are closest together. All right? Either way. All right. Okay, so that's your first one. Now, the numbers that are coming in here. So it says that you single lines come into focus and you read a +4. All right, so that is your first number there. That's your front number, your spherical value. All right, now if both of them came into at the same point, they were both in focus, then this would be 4 sphere. But what they're saying is that's not what happened. Only the single lines, the single lines came into focus first. So that's not spherical. So I start out with a power of +4. I align it, my Meyers on the axis wheel, and it says it comes up to be 167. Okay, there you go. And it tells you that you now bring the triple lines into focus. So turn it the other way, and you come out with a +75. All right, and so I started out with my +4. And now on my second Meyer, so this is my single line. This is my single line, and now this is my triple line. All right, I went from 4 to 3/4. All right, well, the difference between the two, all right, I had to take away 3 1/4 diopters. All right, that is now the value of my cylinder here. And so put your minus 3 1/4 here. All right, and then that's the answer that you're looking for the problem right there. Easy enough. Right. Just do as the problem says, and it's fine. Remember that the definition of cylinder is the magnitude of the difference between the 2 meridians, and that's what you're finding here. This is the highest power of the meridian you found first, the lowest power meridian you found second. The difference between the two is now going to be cylinder. All right, and being as you started from high to low, that's where the minus value comes in, because I'm reducing power. Easy enough. All right, so that's that guy. One down. All right, next guy. Next one says, you are neutralizing a single vision lens with your manual lensometer and find the single lines come into focus first, and you note the power drum reads +1 and the axis wheel reads 54. All right, so I found my first one came into focus. It's a +1, and the axis wheel reads 54. All right, so if it is the single lines, then I know that this is the higher of the power. All right. The triple lines come into focus next with a power of -2 1/4. All right, so -2 1/4 is what came in next. So I started out with a +1. All right, that was the highest power, right? That was the highest power. And now I've now found the lowest power here. All right, well, what's the difference between the two here? Well, I started out with 1. I go 1 diopter to get to 0, and then I go an additional 2 1/4. See what I'm saying? We're on a number line here, right? Here's my 0. All right, I started over here at +1, and now I'm over here at -2 1/4. All right, so I had to go 1 just to get to here, and then I had to go 2 1/4 to get to here. All right, and so the difference between the two is now 3 1/4. All right, 1 plus 2 1/4, and to get from here, so let me get that glare out of there for you. Sorry about that. And to get the to go from here, this was the higher, this is the lowest, therefore it was minus. And once again, minus 3 1/4. All right, and there's your answer to that guy there. Try to keep that guy in the focus if he comes in for you. All right, so now that was number 2. All right, number 3 is over here. You are using a lensometer to neutralize an unknown single vision lens. By the way, it's always saying single vision lens. What does that mean? Always, you're going to need to understand what the questions mean. Single vision means it's not a multifocal lens. So single vision versus multifocal. So not a bifocal, not a trifocal, not a progressive lens. That's what they're telling you. All right. Different ways of reading those lenses in your lensometer, your phosiometer. All right, single vision is just the easiest way to do it. You focus your single lines first, and the power drum reads -2 1/4 or 275. Let's see, you are reading your lensometer to neutralize an unknown single vision lens. You focus your single lines first, and the power drum reads -275, and the axis wheel reads 33. All right. And you then focus your triple lines next, and it reads plus 0.25. Okay. And on the power drum, what is the power of the lens? Well, all right, so I started out with a -275, and then I went to a +2 1/4. Well, to go from 275 to 2 1/4, I have to travel once again, right? There's my number line, there's my 0, here's my -275, here's my +1/4 over here. I got to go 275 this direction and another quarter there. So the magnitude of the difference between them is 3. All right, that's my answer here. But which way did I go? All right, and see, when I started out, when I found the 275, the problem says you focused your single lines first. Well, that's not true, right? Because this is now the lowest power, right? You didn't find the highest power, you found the lowest power. And so this is now the lowest power here, and this is now the highest power over here. All right, although the magnitude of a quarter is less than 275, its value is plus. So its curvature, its dioptric power is greater. You're going in a positive direction. And so what you found out here was a plus. That's the prescription. Now, oh my God, it's in plus cylinder. What am I going to do? All right, well, it's not a big deal. Just convert it. I mean, if the answer if your answer needs to be in plus cylinder, boom, you're done, right? If your answer needs to be in minus cylinder, all right, well, you could start over again, go back in and redo everything. Or if you trust your lensometry readings, then just convert this into minus cylinder form, right? And so the trick to do that, whether you know it or not, I'm taking my 275 and I'm doing 3. All right, the difference between those two is 0.25. The axis in the other form is going to be 90 degrees away from that. All right, so that's going to be 123 over here. And then I'm going to change my sign here, so that's now going to be a -3. All right? And so if you think about it, just go back to what you were doing here. You were just working backwards. That would be 0.25, right? That's what you wanted, was your highest, right? And here's your lowest, which was your -275. And to go from there, I got to go a quarter plus another one there, and there's my -3. All right, and then why did that? There we go. And that's a -3. All right, and so that's your value over here. So either one of these are the, the answer. It depends on, there's no difference between the two of those fellows there. All right, it's just one's in plus cylinder form and one's in minus cylinder form. And, if you need to find an answer, granted, this is generally the way we write stuff, but the other answer is not wrong either. And so that takes you to number 4, right? Number 4 says, in the above question, what mistake was made during the procedure? What was made during the procedure was you brought the triple lines in first instead of the single line. Well, I don't know if that's a mistake or not. It's just, either way, as long as you know how to fix it or you know what the numbers mean. That's what I was saying. Understand what the machine does. Understand what the machine does, and then you understand what the answers are. It's not magic. It's just the machine. All right, if you're going to use a tool, understand what the tool does. And so that is the end of the lensometer questions, and then we'll move on to the questions involving center thickness. Okay, so we're talking about center thickness and edge thickness. All right, and all this has to do also is the concept of sagittal or sagittal depth. Okay, all right. Recall we have a circle. Circle has some sort of curvature to it. Okay, I'm going to just cut that curvature in half like that. All right, and so this circle has some sort of radius of curvature. Okay, and that radius of curvature is what you define also as, or its inverse rather, is the dioptric power of that surface. All right, and so all lenses will have some sort of curvature to it. All right, I have some curvature in this direction. All right, I'm going to make the back of it be plano or flat. Okay, we're going to say that this is a plus lens. And I'm going to have a curvature that goes in this direction. I'm going to make the back of it also flat. And I'm going to say the overall power of this lens is going to be negative. All right, so this is a convex plano lens, gives me positive power. This is a concave plano lens, gives me a negative power. All right, and so in this case, this is made up of a circle of some sort. This is also made up of a circle of some sort, and then this guy has some sort of radius of curvature, and this guy over here also has some sort of radius of curvature. All right. Now, this can be expanded out further, right? It should be the difference between the two indices of refraction divided by the radius of curvature. That's the more accurate way. But we have something to do with these, the radius of curvature. These are how lenses were originally made, by the way. You would take a glass blower, so to speak, and they would make a glass sphere. Okay, so this is in 3 dimensions, it's a sphere. And then you would take a circular stone and you would rub ever so gently for ever so long until you actually carved out a little circle that would look like a lens to you. And that the curvature of this sphere would be the same as the curvature of this lens. All right, and so both of these things would have the same amount of power. I brought them both into focus for you here. Both of these are going to have the same amount of power. That little guy there and this big guy here are going to have the same power. And so when you're looking at a lens, it's kind of hard to tell the circle or the sphere that lens correlates to, or the radius of curvature. So we need something else to correlate that to. All right, and what that thing is going to be what we call the sagittal depth. All right, this guy over here has some sort of radius of curvature associated with it, but we don't really know what it is. We can also describe the linear distance from here to here. All right, so the depth of the curvature, so to speak, that is part of our lens, and we know that as the sagittal. All right, or the sag, which is like the slang word to use it. All right, so the sag or the sagittal that we'll use. And so we need to be able to determine what that sag depth is. All right, now how are we going to do that? All right, well, I have my circle here. It has some sort of radius of curvature. I'm going to make it a little bigger here. All right, so it's easier for you to see. All right, so I have a nice circle here. That's my center of curvature there. Therefore, this all the way up to here, this is now going to be my radius here. All right. I'm going to do the same thing. I'm going to cut a piece of this off to make a lens. All right, so convex plano. Okay, from here to here, from this distance to this distance, this is now the diameter of my lens. Go from this point to this point. All right, which means that this one of these sides here, this guy over here, is now d over 2, 1/2, right? So if this is the distance from here to here, and this is my radius of curvature, I'm cutting this fellow in half right up the middle. Then this distance is 1/2 of the diameter, and from here to here is another half of the diameter. So this side here is d over 2. All right? And so this guy always has the same, the same radius. If it's radius of curvature here, it's the same radius of curvature here, and it would also be the same radius of curvature from here to here. All right, so this guy here is also the radius of curvature. And what did I create here? Ooh, look at that. I just made myself a little right triangle there. All right, one of the sides is d over 2. Okay, one of the sides is r. Right, so the hypotenuse is r. The adjacent side is d over 2, and the opposite side, what could the opposite side over here? Well, from here to here is the radius, right? Except from here to here, from this distance here to this distance here. That's what I just defined for you as the sag, the sagittal depth, which means that this small side here is the radius of curvature minus the sagittal depth. Easy enough. So I have one side, hypotenuse is the radius of curvature of the original circle, the curvature going off here. One of the sides, the adjacent side, is d over 2, 1/2 of the diameter, and the opposite side is the radius of curvature minus the sagittal depth. All right? And then all I have to do is, right, so c squared equals a squared plus b squared, right? And so, excuse me, so it would be r minus s. I'm going to square that fellow. The other side we're going to deal with, he's going to be the radius of curvature side. I'm going to square that guy also. And then the other one, which is going to be my d over 2, that value I'm also going to square. All right? And so that's one side that you're dealing with here. All right? And what I'm going to do is solve this equation for s. That's the guy I want. So I want a sagittal depth, or I want an equation that will give me the sagittal depth. And when I solve for that guy, that's going to be d over 2, that value squared. All right, and it's going to be, once again, what we were dealing with before, which was this value over here. So I'm going to substitute over here. So I need something to substitute for the r, the radius of curvature. And that's what I'm going to do here, d n minus 2, n minus 1 over the r. And so this r, I'm going to throw this guy up here. And this is the n minus 2 over the n minus 1, and my big D goes in the bottom. So this guy here, I'm going to substitute in for my R over here. All right, I'm going to solve for my S, and I'm going to keep my diameter in check. All right, so the sagittal depth is half of the diameter squared times the dioptric power of the lens divided by twice n2 minus 1. What does that mean? What's the 1? Well, the 1 is making the assumption that where the light is coming from is air. All right, so it's actually n2 minus n1. All right, but we're assuming that you have a pair of glasses or a lens that's not floating in water or in a bucket of oil. It's in air, and so we generally just take this n minus 2 and then make that a 1 just to simplify. All right, and so that is your formula for the sagittal depth. All right, now you have to memorize formulas. I understand that. If you can memorize stuff, that's great. But once again, formulas are not pulled out of somebody's butt. They actually mean something, and that's where it comes from. And it's just basically deriving. If you remember the circle and figure this out, you can derive that formula yourself. You don't need to memorize things. All right. And so if you get in a pinch, just think for a bit, and you can work it out. But anyway, that is your formula for the sagittal depth, and that's one of the main formulas you're going to use to solve for these equations. Otherwise, they're just plug and chug formulas. What did you use? What did you learn from that? You didn't learn anything from that, all right? This whole point of this exercise is for you to understand what you're doing. And that, my friends, is understanding what you're doing. Okay, let's flip this fellow over here, and then we'll go back to your problem set over here. So it says, what is the edge thickness of a lens with the following dimensions? All right, and it tells me, this is problem number 5 we're doing here now, all right? And so it says that the index of refraction of the material, that would be your N2, that's going to be a 1.53. They're telling you that the diameter of this lens is 50 millimeters. So 0.50, that's in meters. Okay, I'm a meter guy. Whatever units you want to use, understand that you need to keep your units straight. All right, the center thickness of the lens is given to you as 1 millimeter, 0.001. All right, once again, that's in meters, and that the dioptric power of the prescription is given to you as a -10. Okay, -10 diopters. All right, so that's a setup for number 5. All right, now, how do we figure out what center thickness and edge thickness is? I'm going to go back again a little bit here. I'm going to draw another picture for you here. All right, and so I'm going to go back to my plus lens. All right. And so my plus lens looks like this. Lenses are made from something called blanks, all right? And blanks are kind of like hockey pucks, all right? And so that's what I have here. I have a positive curvature on the top, and then I have a hockey puck on the back. So this was the original picture that I showed you of the convex plano lens, right? That's going to have an overall plus power to it, all right? And so from here to here, the entire depth of this thing, that is now the center thickness. This is the center of the lens, right? From here to here is the thickness. So this is the center thickness of a plus lens. Right? From here to here, this is the edge thickness of a plus lens. That is the piece that kind of fits into the frame, so to speak. All right? And the distance from here to here is the sagittal depth, right? That's not the curvature of the radius of curvature that made that entire circle. That's not what that is. That is a linear value here. That linear value correlates to that radius of curvature, and because that's what we just derived over here, that's where we had that correlation. So we're looking for a correlation of a linear number that correlates to the radius of curvature. All right, and so that's where that value came from. All right, so for a plus lens, if you look at it here, the center thickness of a plus lens, what is that equal to? Well, that's equal to the sagittal depth plus the edge thickness. All right, easy enough. Boom, there's your formula. Look at that, you're deriving formulas on your own now. Don't tell anybody, it'll get you in trouble. I'm going to draw the minus lens that we had here, right? And so I'm going to make my same square hockey puck on the back. All right, so this is now a concave plano surface that's going to have a quote-unquote negative value associated with it. All right, well, what is this? So from here to here, that's now going to be the center thickness of this lens. All right. Note that the center thickness of a minus lens, now we're talking as long as the powers are the same, as long as these curvatures are the same, the center thickness of a minus lens is always going to be thinner than the center thickness of the plus lens, or the center thickness of the plus lens is always going to be thicker or greater than the center thickness of the minus lens. What's here to here? From here to here for a minus lens, that is now the edge thickness. That's the thing that's actually going to fit into the frame itself. Note that the edge thickness for a comparable minus lens is going to be significantly thicker than that of a plus lens. All right? And so what's the sag depth? Well, the sag depth is from here to here. So this is now the sag depth over here. All right, so that's the linear value correlating to the curvature. All right, so for a minus lens, all right, and so this is for this value over here was for a plus lens. For a minus lens, the edge thickness is now going to be equal to the center thickness plus the sagittal depth. All right, there's your two formulas. All right, and you just derive them on your own. Great. You want to memorize them, that's fine. You understand what they mean, and then you can recall them 30 years from now, my friends. It's that easy. Okay. All right, now we're going back to problem 5 here. All right, so I'm dealing with a minus lens. So this is the This is what I need to deal with over here. All right, now, but first I need to do this, I need to know the sagittal depth. I'm given the edge thickness, I'm given the center thickness, okay? And I'm giving values that I can determine the sagittal depth, and that will give me my edge thickness, all right? And that's what the problem is asking for. What is the edge thickness? That's the question that we need to determine. All right, well, let's figure it out by figuring out what the sag is first, okay? And the sag is going to be 1/2 the diameter of the lens squared times the power of the lens divided by twice the index of the refraction, what the thing is made out of, minus the index of refraction, what the thing is in. All right, and so the diameter of the lens was given to you as a 50 millimeters. Divide that by 2, square it, times that by the power, which is a -10. All right, divide that by twice the indice of refraction, what it's made out of, 1.53. And they didn't tell you we're in the bottom of a swimming pool, so we're going to make the assumption that you are in air. Okay, there you go. Now, just do the math. Excuse me, do the math, and what your sag depth is going to come out is 0.00589, okay, and that is in meters, all right, and so there you go. I had like a glitch there. All right, so 0.00589. All right, now that is in meters. All right, so if you want to go 1, 2, 3, that's 5.89 millimeters. All right, whatever works for you. But that's our sag depth. All right, our edge thickness, right, this is a minus lens, so our edge thickness is equal to the center thickness plus the sagittal depth. I just found out that the sagittal depth is 5.89 millimeters. All right, the center thickness was given to me in the problem as 1 millimeter. That means the edge thickness is 0.00689 meters or 6.89 millimeters. Whatever units, I believe this is the units that they want in the problem, all right, but whatever units they would want. They could also say 0.689 centimeters. That would also be the same correct answer. All right, but that's the answer that they're looking for problem 5. All right, remember this, okay, and you need to memorize that. You can either memorize if you're a memorized person or derive them yourself, however you want to do it. All right, so that is problem number 5. All right, problem number 6. Very similar. Excuse me. Problem number 6. What is the edge thickness of a high index lens with the following dimensions? High index, what does that mean? Well, the purposes of this, it means anything greater than what you would think would be for crown glass or CR39. All right, so they give you something that has a 1.71. All right, this is number 6. They're telling you that the index of refraction of the material is now 171. They're telling you that the diameter of the lens is going to be 50 millimeters, so 050, right, 50 millimeters. The center thickness of the lens is given to you as 1 millimeter, and that the Rx, again, the power, is going to be a -10. All right, and so this is the same lens. These are the same parameters that we were using before, right? Here's the other problem, right? These numbers are all the same. 0.5 millimeter, 1 millimeter, 50 millimeters, 1 millimeter, -10 on the power. The only thing difference is that you went from a 1.53, okay, to a 1.71. So you increased the indice of refraction. All right, that's the only difference in the problem. Well, if I increase the indice of refraction, that is in the denominator here. If I make this number bigger, that's going to make this number smaller. All right, if I make that number smaller, it's going to make this number also smaller because the center thickness is the same. All right, that is the point. That's one of the reasons why you may choose to make something out of a higher index material. Higher index material means that it is going to bend the light or refract the light in a more efficient fashion, so the lens could actually be thinner. Okay, if the lens is thinner, then the edge thickness is also going to be thinner. All right, and so once again, you do the math, you can do the sag. The sag is the only thing that's going to be different in this problem. So the sag is going to be half of the diameter, square it, times the power of the lens, divided by twice what the lens is made out of, minus what the lens is in. And so in this case, it's going to be, excuse me, 50 millimeters divided by 2, square that. The power of the lens is a minus 10. Divide that by twice the new indice of refraction, which is the 171, minus the air, which is 1. And when you do the math on that guy, excuse me, that guy comes out to be 0.00440. Okay, and so that is your new sag. All right, that sag is thinner than the sag that you got from the other problem. All right, so the edge thickness for a minus lens, we're dealing with a minus lens here, right? Minus lens. Edge thickness is a combination of the center thickness plus the sagittal depth. You just figured out what the sagittal depth was. That was a 440. I'm off the page here. Let me bring in 00440. And the center thickness, once again, was your 1 millimeter. So in this case, it's 0.00, and then that's going to be a 540. All right? And so, or you could say that that is 5.40 millimeters. All right? And that's the answer to the problem there. Now, you know that this answer for this problem, because this number is greater, you know that the edge thickness has to be less, which means the answer to this problem has to be less than the one that you had previously, right? Remember, this is an optics class. This is not a math class. Do not get optics questions wrong because you make math errors. Always have a way to double check yourself. The original edge thickness was 689. You know the answer has to be less than 689, and the answer that we got for this problem is 540. All right, that's great. That follows. So what does that mean? That means you got a half a chance that you actually did your math correctly. If you got an answer that was greater than 6.89, all right, that answer is obviously wrong. Okay, what would be the most common reason why you would get a wrong answer? Because you made a math error. Always understand the concept and know what the answer is before you attempt to do any math. That's simple. Alrighty, so that was number 6. All right, number 7. That's what we're doing over here now. So this is now number 7. A lens has the following. They tell you that the power is now a minus 450, a minus 3, and the axis is 80. At which meridian is the lens the thickest? Okay, where is the lens the thickest? Which meridian is the lens the thickest? That's where they want to know. Okay, well, what would that be? All right, well, think about it for a second. Where would the lens be the thickest? Here's your formula here, right? All right, so it doesn't matter. What's the center thickness going to be, right? This is going to be a lens, okay? It's going to have some sort of maximum curvature. It's going to have some sort of minimum curvature, all right? Doesn't matter where those minimums are. The center thickness is always going to be the center. The center thickness of this meridian and the center thickness of this meridian are the same. There is one and only one center thickness, all right? Now, what we're worried about is where is the edge going to be the thickest? Is it going to be here or is it going to be here? Which one? All right, well, where's the edge thickness going to be the greater? This is a minus lens, right? Edge thickness, all right, is the center thickness plus the sag. All right, center thickness is going to be the same. Doesn't matter which meridian, center thickness is going to be the same. The only thing that's different is going to be the sag. All right, well, let's take a look at the sag. What is the sag a combination of? The diameter. Is the diameter change between the two meridians? No, it's exactly the same. Does the power change between the two meridians? Yes, it does. All right. Does the indice of refraction, is the lens made out of anything different in one meridian to the other meridian? The answer is no. Is one meridian in any other material? Is one in water and one in air? No, that doesn't make any sense. All right, so all these variables are the same. The diameter and the indices of refraction are the same. The only variable that changes is the power. And you'll note that the power is in the numerator, okay? Which means as this power increases, this sagittal depth will also increase. As this number is smaller, this number will also be smaller. Well, it's asking me where is it going to be the thickest? So where is the sagittal depth also going to be the greatest, right? It's going to be the greatest. And so that's going to be the one that has the most power. Which one of these two meridians has the most power? The 450 or the 80? All right, so one of these meridians has a power of 450, all right, and that is going to be at the 80th, okay? And the other one has a power, well, what is this? What is this number? This number is the magnitude of the difference between these two guys here, all right? Between the maximum and the minimum. And so if the difference is 3, minus 3, and one of them is 450, then the other one is going to be a minus 750, all right? And that power is going to be that's going to be 90 degrees away from here, and that's going to be the 1/70th. Well, which one's bigger, 450 or 750? Boom, there's your answer. Okay, then we're done. You see, did we do any math? We didn't do any math. All right, all you had to do is understand what you're talking about, and the answer comes to you. All right, don't need to do any math. All right, now, according to the problem, excuse me, it wants you to know, find the edge thickness now along the two. All right, now they want a numerical value for the edge thickness. So, all right, fine, I have to do some math. All right, but the original question didn't say anything about finding edge thickness. It just said, at which meridian is the lens edge the thickest? That's all. There's only two meridians, right? And there's only two possible answers. I didn't have to actually find a math answer. But now, in any case, I know what the answer is. It best be the one at the 1/70th. So now I'm going to do math, and if it doesn't come out to be the 1/70th, I know I made a math error. Okay, once again, always have some way of double checking yourself before you attempt to do any problems. All right, so we'll try it. We'll do it both ways and see which one comes out. All right, so the sagittal depth, and I'm going to do this for the excuse me, for the 1/70th. So this is going to be at the power that's along the 1/70th. And so once again, it's going to be sagittal depth is half of the diameter squared times the power divided by twice the difference between what it's made out of and what it's actually in. All right, so the diameter of the lens, they're going to give us values for those things there. 7. Here we go here. They're going to tell you that the lens blank is 60 millimeters. That's the same thing as diameter, right? So that is 60 millimeters, 0, 6, 0, right? 1, 2, 3, 60. The indice of refraction of what it's made out of, that's going to be the N2, excuse me, that's going to be 1498, and the center thickness is given to you in the problem of 2.2 millimeters. So 0, 0, 2, 2. 1, 2, 3, 2.2 millimeters. All right, those are the values that you're going to have to deal with. All right. Didn't tell you that you're in the bottom of a swimming pool, so the N1 is going to be air. All right, so in this case, I have my diameter, which is 060. I'm going to half it. I'm going to square it, and I'm going to times it by the power at, with, or along the 170, and that's going to be my minus 750. And I'm going to divide that by twice what this thing is made out of, given to you on the problem, as the 1.498 minus the air, which is a 1. All right. Excuse me. Do the math on that guy, and he comes out to be 0.00677, or 6.77 millimeters, if you like it that way. All right, so that is at, with, or along the 170th. All right. And so we're going to do it now for the other meridian, which is the 80th. All right, once again, it's just going to be sagittal depth is equal to half the diameter, square it, times the power, divided by twice the difference between what the thing is made out of and what it's sitting in. And so the math on that, this number is the same, 60 millimeter diameter, half it, square it. Now the power at, with, or along the 80th is a 450, right? That's the number that's smaller, right? 750 was the big one, 450 was the small one. Divided by twice what it's made out of the same thing, 1498, in the same thing, air, and the 1. Do the math, excuse me, for that guy. And then he comes out to be 0.00406, and that's the same as 4.06 millimeters. All right, and so that's at, with, or along the 80th meridian. All right, well, which one? And what? So back to the same thing. What do they want to know what the thickest is? Well, I got a choice of 6.77 millimeters, and I got a choice of 4.06 millimeters. Well, 6 is bigger than 4, and so there's your answer. And there it is at 70, and that's the answer that we got here, right? And so the answer we know it's going to be is the same answer we did when we did the math. Got a half a shot at getting the problem correct, all right? Always make sure you know the answers before you attempt to do any mathematical problem. Okay. All right, so that was number, excuse me, that was number 7. Let me get a fresh sheet of paper here. And there we go. Now we're going to do number 8 over here. At which meridian is the lens the thinnest? See if that comes into focus for you there. All right, there you go. All right, so now this is number 8. All right, and for 8, we have a power that is going to be now a -7, a plus 150. Ooh, that's in plus cylinder form. Ooh. Let's see, and they want to know where is the thinnest, and so that's going to be the question. All right, the other one, they want to know which meridian was the thickest, and they want to know which one is the thinnest. And they're going to give you some parameters, and the parameters are going to be the same, right? It's going to be a 60 millimeter blank, so that's now the diameters. It's made out of the same 1.498, and the center thickness is given to you as the 2.2 millimeters, 0.022, 1, 2, 3, 2.2. All right. And now, in this case, we want to know what is the thinnest. All right, well, same idea. This guy's going to have 2 meridians, and so the 7, so I'm going to have one that has a power of a -7, and that's at, with, or along the 165th, all right? And so to get from here, this is a plus 150, so that's the difference in magnitude between the two. Well, if this is a 7 and the difference is 150, in other words, I have to go a plus 150 to get the next one, which means I'm reducing the magnitude of this guy. So that's going to be 5.5. Right? And so we're back over here. So this is 7, all right, less 150, and that's going to be 5.5, minus 5.5, right? To get from here to here, to get from here, I had to add 150. If I add 150 to a -7, that gives me a minus 5.5. And that power is going to be at, with, or along 90 degrees away from that guy, and that's going to be 75, right? 90 and 75 is 165. Now, in this problem, they want to know what the thinnest is. Well, we're back at the same thing, all right? Everything is the same between these two, right? We have two meridians here. One is the steepest, one is the shallowest. The center thicknesses are exactly the same. All I want to know what the edge thicknesses are. They're made out of the same thing. The only thing that's different is the powers, which means the only thing that's different is going to be the sagittal depth. What is going to be the driving function? Well, it's going to be the power. And so the one that's the thinnest is going to also be the one that has the least power. All right, bingo. There's your answer. We're done. All right. But the problem's not done, because then once again they want to know what are the thicknesses in the two meridians. Well, we'll do the math. Well, when we do the math, the smallest one best be the 75th. All right, so let's do the 165th first. All right, and so excuse me, I need to know what the sagittal depth is going to be. Excuse me. All right, and that is going to be sagittal depth. Once again, that's half of the diameter. Square it times the power in that meridian divided by twice the indice of refraction of what it's made out of minus what it's sitting in. Right? And so this guy over here is going to be the 0.60, half it, and then square it. The power, we're doing the 165th, and that's going to be the minus 7. That's going to be the power that I want over here. Let's bring him into focus for you here. There you go. I'll keep my finger there for you. And then divide that by twice what it's made out of, which is the 1498 minus the 1. All right. Solve for that guy there, and he comes out to be 0.00632. All right. And so that's one of your sagittal depth. Your other sagittal depth, we're going to do it over here for the 75th meridian. And once again, that's going to be half the diameter, square it. Why am I writing this again and again and again? I think I know what it is, but why am I writing it again and again? Because that's the way you memorize stuff. Again and again and again and again. All right, so that's why I'm writing it out there for you. All right. If you're so smart that you don't need to do that, that's great. 0.60 divided by 2, right? Same numbers. The only thing different is this. Now I want the power at, with, or along the 75th, and that's going to be my minus 5.5. I'm going to divide that by twice what it's made out of, the 1498 minus the 1. All right, and if I do the math on that guy, my sagittal depth is going to be 0.0496. Okay, and then once again, this guy here, so here's my check. I got 4.96 millimeters. All right, and I have a choice of 6.32 millimeters, and it's asking me what the thinnest is. That guy's the thinnest. And what does he correlate to? He correlates to the 75th. That's the answer that we came up from the beginning. Okay. Now they wanted to know what the edge thickness was. Great. Okay, so the edge thickness is going to be the center thickness plus the sagittal depth. It's going to be the same over here. The edge thickness is equal to the center thickness plus the sagittal depth. The center thickness was given to you in the problem as the 2.22 millimeters. And then this is going to be the 0.0496 over here. This guy is going to be the center thickness, the 0.022 plus the 0.0632. All right, you add, excuse me, you add those two together, and that is, 0.0852, and it's 8.52 millimeters, right? There's your one answer there. And then this guy over here, you add these two together, and that's going to be 0.0716 or 7.16 millimeters. All right, once again, which one is the smallest? That guy's the smallest. The smallest, the smallest, the smallest, or I'm sorry, the thinnest, and the thinnest. Okay, it always comes out to be the same answer. All right, but in the problem, the second question she wanted to do what the edge thickness was, and this would be the value for the edge thickness in the 2 meridians, and then the original answer is obviously the 75th meridian. All right, easy enough. So that is now 8. All right, and so now we'll go on to problem number 9. My God, it never ends. What is the center thickness? This is number 9. Go back to your problem set over here. Now we're down into here. Number 9. What is the center thickness of a +7 lens? Oh my, now it's a +7 lens. Does it work the same way? Sure, it works the same way. All right, except now you're going to be dealing with, for a minus lens, you're going to notice they're always going to be asking you about the edge thickness, all right? Because that is going to be the parameter that is going to be most problematic for you. Having those ugly looking thick lenses on a myopic prescription, all right? What's it going to be on a hyperopic prescription or a plus lens? Well, it's going to be the nasty thickness of the lens itself. So those are going to be the primarily the two parameters that you're going to try and limit, okay, from a cosmetic or a functional standpoint. All right. You never really have to worry about the edge thickness on a plus lens, other than it could be too thin, all right, to fit into certain types of lens when you get into a half rim, the one that has a little piece of wire underneath it. You have to cut a groove into it, right? Where that would be an issue for you. But you're generally really not worried about the edge thickness. And then the center thickness of a minus lens, you're really, it's always going to be skinnier, so you're never worried about that being too thick. You might be worried about that fellow actually being too thin from a safety or a structural integrity standpoint. But they'll tend to be worked out for you. So you'll notice that for the minus lenses, they're always worried about the edge thickness, and the plus lenses, they're always worried about the center thickness, and that correlates to the formulas that we derived previously. All right, but in 7 we have, in 9, we have what is the center thickness, and that's what they're asking me for. What is that guy going to be? All right, and they're telling me that the power of the lens is +7, and it's made out of a 1.67. They're telling me that the blank size, which is going to be the diameter of the lens, and that's going to be 55 millimeters, and that the edge thickness they're giving to me in the problem, and that's going to be 3/4 of a millimeter. All right, so that's going to be 0.00075. There you go. All right, that is 3/4 of a millimeter. That's called a knife. That's what that thing's called there. All right, so interestingly enough. All right, but that's given to you. All right, so now 9. What is the center thickness? Okay, easy enough. All right, so once again, the center thickness of a plus lens, that's going to be a combination of the edge thickness plus the sagittal depth. All right, the edge thickness is given to you in the problem. That's the 0.00075 or 1, 2, 3, 3/4 of 1 millimeter. Now I need to figure out what the sag is. All right, well, the sag is half the diameter squared times the power, excuse me, divided by twice what it's made out of minus what it's in. All right, and so diameter was given to you in the problem as 55 millimeters. Half it, square it, times it by the power. It's a spherical lens. There's only one power, right? So there's a +7, and then divide this guy by twice. It's made out of a 1.67 material. Oops, minus. They didn't tell you we were in a swimming pool, so that guy's going to be a 1. All right. You can do the math for that guy. Excuse me, and he comes out to be 0.00470, or you could say 4.70 millimeters. All right, that is now the sagittal depth. So I'm going to take that value there, I'm going to stick it up here, 0.00470. Excuse me. Ooh, man. Add these two guys together. I'm sorry, this is not 47. This is not 470. My bad. I was ahead of myself. This guy is 0.00395 or 3.95 millimeters. All right, and that's the value that I want to put up there. That is a 395. And when you add those together, that comes out to be the 0.00470, or another way of saying that is 4.70 millimeters. And so that is the center thickness, and that's the answer to the problem. Sorry about that. I jumped ahead of myself when I looked at my math problem there. All right, so that is number 9, and then we have, 1, 2, 3, 4, wow, 5 more. Okay. Next ones we're going to go into frame diameters and along those lines, boxing numbers. All right, so we'll do that when we come back. Okay, so we're back for the last part of this problem set. And to do this, you need to know something about the how frames are sized up and how lenses are put into the frames and in what fashion they need to be. All right, so I'm just going to draw like a generic looking pair of eyeglasses here, right? Very boxy, all right? And so the vertical diameter of the eye wire, all right, from top to bottom here, that's known as the A dimension, all right? The width of an eye wire for one side, that is known as the B dimension, okay? The distance between the two eye wires, okay, or the distance between lenses, tend to call that the DBL. So distance between lenses, DBL is an acronym. Another word that people use that is called the bridge, right? Because it looks like a little bridge between the two, all right? And then this is the temple length over here, right? So from here to here, that's your temple length. All right, and so that is your dimensions of a general frame. And they are given to you in what's called a boxing number, okay? And it's going to be a number, and then another number, and then a third number. And so what do those numbers mean? All right, and so when you're given the boxing number of a frame, the first one here is going to be the B dimension, or the width. And so this is going to be the B, or the width of the eye wire. The second one here, the center, that is going to be the bridge, or the DBL, all right? And the third number is going to be the temple length, all right? So if you look up any frame, it'll give you what's called, and this is called a boxing number. Boxing number is the euphemism that people use to describe that. All right, so it's going to be 3 digits. One is going to be the B. One is going to be the DBL, distance between lenses, or the bridge. And this is going to be temple length. And these numbers are going to not have units to them, but remember that these numbers are all going to be in millimeters. All right, so they're all going to be whole numbers, but their units are going to be millimeters. All right, this guy, for just the way people's faces are, or the size of people's faces and how glasses go, it's going to be 2 digits for the width, or the B dimension, 2 digits for the DBL, and 3 digits for the temple. And so generally we see a 2-digit number, a 2-digit number, and a 3-digit number. And then you know it's a boxing number. All right, so that's basic. So we'll see, when we do the problems, we'll see boxing numbers, and you'll see what I'm talking about. I'll give you the first one for the number, just so you have something to go with. And it's 5216-135. So it's a 5216-135. All right, and so these numbers, they're whole numbers, but you know that the units are millimeters. That means that the B dimension, or the width of a single eye wire, is 52 millimeters. This is the distance between lenses, or the length of the bridge, that's 16 millimeters, and that this is the temple length, which is 135 millimeters. Okay, and for the first purpose of the problem, these two are the ones that we're going to need to deal with. All right, and so because you're going to fit this frame has to fit on a person's face, and you don't know where the eyeballs are going to be. Now each eye wire is going to have a geometric center, okay, something that's going to be dead in the center, all right? And so that is going to be the geometric center of the frame, or the PD, the pupillary distance, so to speak, of the frame, all right? That's just a euphemistic way of looking at it, but it is the distance between the two geometric centers of the frame itself, all right? I'm just going to call that, for our purposes, the PD of the frame. Now, you don't know where the patient's eyes are. Like, what is the PD of the patient? Let's say, sake of argument, these are the two pupils of the patient when they are actually wearing this frame, okay? And so from here to here, this guy here, from here to here, this is the PD of the person, or the patient, all right? And those two are rarely the same, all right? And actually, just the way lenses work, and you'll get this when we do our frame fit lecture, you actually want the PD of the patient to be smaller than the PD of the frame. In other words, you want the patient's pupils to be inside the geometric center of the lens, and we'll learn about why that is. But for sake of argument, at this point, it doesn't matter. But the frame itself has a PD, and that the patient also has a PD. All right. Now, the lens itself, when it fits into the frame, the optical center of the lens must be aligned with the PD of the patient. If that is not the case, then you have what's something called induced prism, which we'll talk about in the lecture. All right. But when I put the lens in, I'm going to have to decenter a lens. In other words, I don't want the optical center of the lens to be here. I want the optical center of the lens to be here. All right. So when I actually put the lens into the frame, it needs to be decentered. It needs to be decentered. In other words, it cannot be in the center, in the geometric center of the frame. It needs to be aligned with the pupils of the patient. And so unless these things work out perfectly, it can be decentered in, and in generally as the lens goes to the nose, or it would be decentered out. Out would mean towards the ears. All right. Now, in general, you really don't want to decenter lenses out, and we'll learn about that in the lecture. You want to decenter lenses in, but at this point we're just doing a problem, so you don't have to know about that. But lenses will need to be decentered at some purpose. All right. Now, if I decenter the lens, in other words, you would think, well, I would want a lens that would just fit inside the frame, right? But if I decenter the lens, all right, if I bring the lens in, because here's the PD of the frame, now here's the PD of the patient, I have to decenter this lens in. If I take this same lens and now move it out here, now the lens is going to be too short. I'm going to have a gap over here, right? You don't want that gap. All right, so the lens actually has to be bigger than the width or the B dimension. It has to be larger, all right? And that actual width of the lens is called the minimum blank size. The minimum blank size. All right, we use an acronym for that, which is the MBS, or the minimum blank size. And what is that minimum blank size? The minimum blank size is, going to be what's called the effective diameter of the lens plus twice the decentration of the lens. All right. All right, what the hell does that mean? I just use a lot of little acronyms in there. Now, all frames are going to have an effective diameter. An effective diameter is going to be the largest. Let's see, I'm going to make my lens like this, right? Now, I need a blank that fills this entire lens, which means I have to take a measurement this way, I have to take a measurement this way, and I have to take a measurement this way. All right, obviously this guy here, the diagonal on a rectangular lens, is going to be the greatest. That would be the minimum blank size. If I had a round lens, that would just be the diameter. Diameter is the same everywhere, all right? And so those two are relatively easy. You get into some wacky looking things, these old style aviator glasses, right? These things that the state troopers still wear, right? Because it makes you look cool. Now, what is that? Is it from here to here? Is it from here to here? That's a funky, you don't even know where the center, the geometric center of this thing is, which is probably down here somewhere. All right, and so that's where it gets funky. And so all frames will have boxing numbers like we talked to, and it will also give you its effective diameter. So it'll be ED, is going to be whatever it is for this. All right, they'll give you that listing, and that's what I'm talking. So effective diameter. All right. Now, when we're talking about decentration, right, we had that gap. All right, which means I have to add whatever that gap is. Right, that's my decentering. But if I add it here, it also gets added to the other side. Does that make sense? If I'm sliding the lens over, not only do I need more plastic here, if I have more plastic here, it's a circle, which means I'm going to have more plastic on the other side. That's where the 2 comes from. All right, so the minimum blank size for any lens, it's going to be the size of the blank that I'm going to cut the lens out of. And then it's going to be round when I'm done, but then it's going to be edged. And edged means that the lens is going to be cut to fit into the shape of the frame. All right. So all lenses, the power is ground into the blank, and all blanks are round. But I need a round enough circle so that when I edge it to fit into the frame, I don't have any gaps on the end. All right, and so that minimum blank size is going to be equal to the effective diameter of the frame. That'll be given to you in the problem. There's no way for you to know it when actually having the frame, plus twice the decentration. All right. And so that's the excuse me, that's the nuts and bolts of doing the problems that way. All right. All right, so let's get to the first problem here. Well, the first problem is also problematic, and there's another piece of information that you don't know what to do, but at least you needed to know how to do that to start with. All right, and so now we are on number 10 over here. All right, so 10 says, what is the edge thickness along the 180th meridian? All right, so I want the edge thickness at, with, or along the 180th meridian. What is that? All right, that's what they're asking me for. And they're telling me that the power of the lens is going to be a -3, a -1, axis 45. All right. And then they'll give me a bunch of parameters. They're telling me that it's made out of, the lens is made out of a 1.6 material. They're telling me that the center thickness of the lens is 1 millimeter, 001, 1, 2, 3. All right. Lost my place here. 1 millimeter, and they're telling me that the patient's PDs, they're monocular PDs. All right, so PD of the patient, and that is going to be 31 over 31. All right, so that is from the center of the bridge of their nose to their pupil, and the center of the bridge of their nose to the pupil. So they're monocular PDs. All right, the binocular PD would just be that together. That would be 62. All right, but in this case, they're giving you the monocular PDs, which would be 31 on each side, which means that the patient is perfectly symmetrical. And they're giving you the dimensions of the frame. They're giving you the boxing number, and that's going to be the 52/16/135. And they're giving you the effective diameter of the frame, and that is 54. And then these numbers, once again, are all in millimeters, all right, by default. All right, and that's it. Okay, easy enough. All right, so I'm given the size of the frame here. All right, so what am I going to do? So I got a 52. So now I have a frame that looks like this, right? And I need to know, this is the center line, right? This is the patient's nose, right? I need to know where the geometric center of the frame is going to be, all right? Well, I'm told that this is 52, and I'm told that from here to here is 16. All right, great. All right, so half of that, excuse me. So I can just add these two together and then take half of them, right? So it'd be half of 52. Otherwise, I could do, I'll do it for you. Do it, right? So 52, so that would be 26, and half of that would be, half of the 16 would be 8, and I add those two together, and that comes out to be 34. Okay, so that's one way of determining what the PD of the frame would be. All right, the other way is it's the same thing. You're just doing 52, add the 16, and that gives me 68, and take half of that, and that gives you 34. All right, you'll note that both of these things are the same. All right, so however you want to work that out in your brain, that's great, but you'll come to the same answer. It's just the same math. All right, and so 34 is the PD of the frame, so to speak. Okay, geometric center of the frame is at 34 millimeters. Okay, and did they tell me what the patient's PD? That would be 31. All right. Once again, I did the monocular PD of the frame, right? It's only half. So I need the monocular PD here. If they didn't give you monocular PDs and they gave you a binocular PD, in this case it would be 62. Take the 62 and half it. All right, that will give you 31. But in this case, they gave it to you monocular, so just use the 31. So the difference between the two is 3. The difference between 34 and 31 is 3 millimeters, which means that if you look at it here, this is the PD of the patient. All right, the patient's face is smaller than the frame, which means the lenses have to go in, which means that decentering, this is now the decentration, that's 3 millimeters in, so to speak, or towards the nose. That's the way I'm going. All right, now the minimum blank size is going to be the effective diameter of the frame plus twice the plus twice the decentration. All right. And so this is going to be the effective diameter was given to you on the problem of 54, and this is twice what you just figured out here, which was 3. And so that's 54 plus 6, or that's going to be 60. That is my minimum blank size. All right, well, what does that mean? My minimum blank size is now analogous to the diameter of the lens. The diameter of the lens, or the blank that I need, is going to be 60 millimeters, right? This is in millimeters. This is in millimeters. All right, I'm sorry, this is in meters, but this is 60 millimeters. All right, so that's the value that I need there. All right, great. Excuse me. Now, I need to know what the edge thickness is. All right, so to determine the edge thickness, I need to know what the center thickness is plus the sagittal depth. All right, the center thickness was given to me in the problem. That is 1 millimeter, and then I need to know what the sagittal depth is. All right, well, to find the sagittal depth, I know it's the diameter of the lens, half it, square it, times the power. All right, but this one's a astigmatic lens, so I'm not sure what the power is. This is where it's going to get sticky, and I'll have to go over that with you. Now, hold on a second. We'll get to that. Plus twice what it's made out of, minus what it's in. All right, so that's going to be what you found here, the 060. That's why we'd have to do all this. We had to do all this mumbo-jumbo to figure out what the diameter of the lens is going to be. All right, divide that by 2, square it. The D, I don't know what that's going to be yet. And then twice what it's made out of. They told you it was made out of a 1.6 material. They did not tell you you're in a swimming pool. Therefore, we're going to assume that N1 is equal to 1. All right. This is the guy that I need right here. What is this guy going to be? All right, now this gets a little funky here. All right, so I'm going to come back to this. All right, I'm going to put this guy over here, and we'll come back to this. I have a prescription that's given to me at a -3, or as, excuse me, a -3, -1. Axis 45, and what they want to know is what is the power, in other words, what is the power at, with, or along the 180th? Why are they asking me that? Why 180th? Well, it's kind of pretty obvious here, because if you look at the frame, most faces are going to be, they're wider than they are shorter as far as frames go, and so I'm always worried about the meridian this way. That's going to be the A dimension, unless you're dealing with John Lennon glasses, ones that are perfectly round. The vast majority of frames are going to be shorter vertically than they are horizontally. And so that's the edge thickness that I'm going to be the most worried about, which is the horizontal, or what the power is along the 180th, which is what I need to figure out. And so that's what they want to know. But they gave me a prescription that doesn't have 180th in it. So how the hell are you supposed to do that? Well, I'm going to tell you, you don't know how to do it. That's why we're going to have another whole freaking lesson here. All right, so let's put this thing onto an optical cross so we know what we're talking about here. All right, so I got 45. I'm gonna call that up here. I'm going to call him the 45. Well, if he's the 45th, then this is the 135th here, right? 90 degrees between the two. This correlates to this, which means that the power in this meridian is a -3. All right, this is the cylinder. That's the magnitude of difference between the two. So to get to here, I had to go from here, but also subtract another 1. So this guy is -4. All right, so that is the optical cross that actually works for here. All right, but what they want to know is what is the power at 180? All right, well, and so halfway between here and here is going to be the 90th, and then 90 degrees away from that, that's going to be the 180th there. All right, and so easy enough. So if this is -3 over here, this is also -3 over here. This is -4 over here. This is also -4 over here. And I'm going to get it because I want to look at, I want the one here. This is what I want to know here. What is this power going to be? All right. And so this is the cheat, all right, that you're going to do, except you have no clue what it is to cheat. All right, now, what is that? So I'm going to figure, well, if this is the steepest and this is the flattest, all right, and this is going to go from -4, decrease, 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 decrease until I get to 3, and then it's going to increase, 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 increase until I get to 4. All right. They want to know what it is going to be at the 180th. Well, the 180th, just by happenstance, happens to be halfway between the two. All right, exactly halfway. All right, because this is 90 and this is 90 degrees. This is 90 degrees here, and then this is 90 degrees here, which means that that's going to be halfway. And if that's halfway through the two, that means this power here is going to be 350. All right, that seems logical to you. All right, but guess what? The only reason that you're able to make that sheet is because it happens to be halfway between. All right. If you wanted to know what it was at the 80th, or you wanted to know what it was at the 110th, you couldn't do that little cheat, because dioptric power is vergence, right? Dioptric power is nothing more than how the light is bent. Vergence is a non-linear function. That is a complete anomaly that you're able to do there. All right? The way that you would actually have to do the problem is by using a formula that we will derive later, all right, which is the power at any given meridian is the power derived from the spherical component of the prescription plus the cylindrical component of the prescription, and the sine squared of the magnitude of the difference between the two. All right, just so you know where we're going. And I'm going to use this guy here. So this spherical component is a -3, plus the cylindrical component from this notation would be a -1 sine squared, and that would be the difference between what I'm doing here. And that's going to be, you know, the difference between 45 and 90. So that's going to be 45 degrees over here. And if you do the math to solve, you have no variables here, right? If you do the math to solve for that, that comes out to be -3.5. All right, and that -3.5 happens to be the same as it is over here. All right, and that is, my friends, an anomaly. This is the way you will need to do those problems. The only reason, if it's any other number than halfway in between. All right, now, that's, as far as I know, you haven't had any lecture on it. So that's why I'm giving you the heads up. But for the problem, we're going to do the cheat, and we're going to come up with the power in the meridian that I want, which is the 180th, is going to be the 350. All right, so now I'm coming back into here. All right, and so the power at, with, or along the 180th, we've determined that to be a -350, and then that's what we're going to put in here. So this guy is now a -350. All right, everybody back. This is the sheet that we used before, right? Nothing's changed here. I just pulled it back. I didn't know what this value was. That's where I got the 350 from. Ooh, excuse me. That's where I got the 350 from over there. All right, so I'm going to do the math on that, and that guy comes out with a sagittal depth, which is going to be equal to 0.00263. All right, that's my sagittal depth. My edge thickness is the center thickness. That was given to me in the problem as the 1 millimeter. The sagittal depth I just found over here, 0.00263, or 2.63 millimeters, right? I add these two together, and right, 1 and 2 equals 3. 363, or another way of saying that is 3.63 millimeters. All right? And that is the answer to the problem. That is the edge thickness at, with, or along the 180th meridian. All right. So this is the context of what we were talking about. This thing here is a future concept. I don't know why it was actually included, but anyway, you learned something new. Look at that, no extra charge. Okay, so that's the answer to the number 10 that we're dealing with. All right. Number 11. Number 11 is we don't have to do that hop, skip, and a jump, because we're actually giving a prescription that is the cylindrical component. It's with the rule. In other words, we're talking about something that's 170 degrees over here. Right, so our new prescription is going to be here. This was 10 with our 45. Oops, not there. Come over, come into focus there, Bubby. 45. Now we're dealing with something that's 170. All right, so now here is number 11. All right, so what is the center thickness of a lens? Center thickness of a lens. That's going to be, center thickness doesn't matter what the meridian is here now, right? Because we're not dealing with edge thickness. So actually the prescription could be whatever the hell it wants to be. It doesn't matter. All right, so what is the center thickness of a lens? And now we're dealing with a plus lens. And so the power is going to be a +6, a -1, and the axis is 170. All right, and they're going to give me some new numbers here. And so the indice of refraction of what it's made out of is 1.70. The edge thickness is given to you as 2 millimeters. And that's given to you 2 millimeters at, with, or along the 170th. And so this correlates with this. So we don't have to do the problem that we did previously, right? We just cut to the chase. So they give it to you where it is. And that's great. Just say thank you. The patient's PD. All right, so the PD of the patient, once again, is given to you as monocular PDs, and that's 30 and 30. Once again, these are all models that you're dealing with. They have perfectly symmetrical PDs. And the frame dimensions, the boxing number is given to you as 48, 20, 140 with an effective diameter of 50. All right, great. All right, so now I need to find out what my minimum blank size is. My minimum blank size is equal to the effective diameter of the lens plus twice the decentration. The decentration. There you go. All right, and so in this we know it's 50 millimeters here. All right, so I need to know what the PD of the frame is. So I'm going to take the 48, which is the B dimension, the 20, which is the distance between the lenses. That gives me 68. I'm going to divide that by 2, and that gives me a 34. So that is for the frame. All right, for the patient, however, that was given to me in the problem, that was 30. I take the difference. Come into focus there, fellas. There you go. There you go. Gotta keep my hand over here. There you go. Take the difference between the 34 and the 30, and that gives you 4. That is now my decentration over here. All right, so this is plus twice the decentration, which we have just calculated as 4. All right, so this is now 50 plus 8, and so that is 58. Ooh, excuse me. And so 58 millimeters is now the diameter of my lens. All right, so the minimum blank size, and that's analogous to the D. So the D is, this is in millimeters, right? So 0, 5, 8, 1, 2, 3, 58 millimeters. That's now my D. All right. So center thickness. They want to know the center thickness. Center thickness is going to be the edge thickness plus the sagittal depth. That's for a plus lens, right? And the edge thickness was given to me in the problem. It is at the correct meridian, so I don't have to worry about that. That's a +2. I got to figure out the sag. The sag is equal to half the diameter, square it, times the power. And so that is going to be, divided by twice what it's made out of minus what it's in. All right, and so this guy, we have now figured out that 58 is the diameter, divided by 2. Square it, times the power. Times the power. I want the power. This is the center thickness at, with, or along the 170th. So I need the power at, with, or along the 170th. This guy correlates to this guy. And so the power that we're dealing with over here is the +6. All right. If you need to put that on an optical cross, go ahead. All right. But the power at, with, or along the 170th is the +6. All right, this is the magnitude of this is the maximum or the steepest meridian, and this is going to be the difference between the two minus, and so the other meridian, which is 90 degrees away from this, which is going to be 80. All right, and that's going to be a +5. All right, but the +6 is at, with, or along the 170th. That's why the 6 is over here. Divide that by twice what this thing is made out of. They told me that what it was in the problem. Was that 1.7? Let me just double check that. Yes, it was 1.7. And they didn't tell me I was in water or in oil, so I'm just going to have -1. Right. And so, ooh, excuse me, do the math on that. And that kind of comes out to be 0.00289. 0.00289. Another way of saying that is 2.89 millimeters. All right, and so that guy comes over here. 0.00289. Add those guys together, and so 0, that's going to be 0.00489 or 4.89 millimeters. And that is the center thickness. That is the answer to the problem there. Okay, easy enough. All right. Now that one was significantly easier than the first one. You still had to do the frame stuff, right? That's what you're learning. That's ophthalmic optics. But you didn't have to do the figuring out what the power was in the meridian like you did in the other one. That's something we're going to get into in I believe it's geometric optics. Everything has a little name around here. All right, but you didn't have to do that in that case. All right, so that was just there. Now, number 12 is going to be same problem, right? Same patient, but now what they're going to do is they're going to swap frames out, right? For whatever reason, the patient tried on this frame, didn't like the way it looked, all right, and then all of a sudden they changed their mind. Okay, great. So what? All right, so now we're going to have to figure out what is going to be the new center thickness, okay, if we're going to keep all the parameters the same, all right, except now we're going to use a different frame. And the new frame is going to have a boxing number of 46, 18, 140, and an effective diameter of 48, all right, so it's a smaller frame, physically smaller frame. All right, so we'll take the B number, which is the 46, we'll take the DBL, which is the 18, add the two of those fellows together, that gives me a 4, and that gives me a 6, so 64, all right, and that back to here, I'm going to take half of that, and that gives me 32, right, that gives me 32, and then remember the patient's PD is 30, and so that gives me a decentration, so this is for the frame, this is for the patient, and then this is my decentering. And so that gives me a 2 for the decentering. All right, so my minimum blank size for this guy, minimum blank size, is going to be the effective diameter plus twice the decentration. All right, the effective diameter for this frame is 48 plus twice the new decentration, which is 2. And so that's going to be 48 plus 2 times 2 is 4. And so it's going to be 52. And so my new D is now going to be 52 millimeters. Okay, 52 for the new problem. All right, so once again, the center thickness is going to be the edge thickness, and the edge thickness is the same. And the problem, use the same RX, mon PD index, and the new center thickness is what I want, but the edge thickness is going to stay the same. All right, that's going to stay as a 2, but now I'm going to have this new sagittal depth because the curvature is going to be different, and the sagittal depth is going to be half the diameter, square it, times the power, divided by twice the difference of what it's made out of and what it's in. All right, now this is the only thing that's going to be different here, which is going to be 0.052. Think about it for a second, right? Everything else is going to be the same. The power in 170th remains the same. What it's made out of remains the same. What it's in remains the same. The only thing different is the diameter. All right, and the diameter, because it's a smaller frame, is going to be smaller. It went from a 58 to a 52. All right, what do you think is going to happen to the sagittal depth? Think about that for a second, right? So you know what the answer should be before you already started. All right, what it's going to be over here. So I have my 52 divided by 2, and then I'm going to square it. And then the power, the same ideas on the 170th, that's going to be the 6. All right, and then over here, that's still going to be the 1.70 minus, and that's minus the 1, and that's going we have to double that. But that's what it's made out of, and we're in air. All right, solve for the ooh, excuse me. Solve for the sagittal depth along that fellow. Ooh, excuse me. Solve for the sagittal depth on that fellow, and that guy comes out to be 0.002. 289. What did I do? Oh, I'm sorry. I mixed these up for you here. My bad. That guy is going to be, I actually just answered that one for you there. All right, this guy here, when we did the math for, I'm going to go back a bit. Sorry about that. This answer is going to be for the, I kind of mixed them up for you here when I was checking for my math answers. So this is the, we were trying to figure out the sagittal depth for the 58 millimeter here. When you do the sagittal depth for the 58, that comes out to be 0, 0. I'm sorry, that is going to be 360. That's a 3, that's a 6, and that's a 0. So that's actually going to be 3.60 millimeters. And that's the figure that you're going to put up in here. 0, 0, 3, 6, 0. And so when you add the two together, that's going to be a 5, 6, 0, or 5.60 millimeters. All right, over here, that's where I got the answer to this one. This guy, when you go to do the math on this guy comes out to be your 289, 0289. Sorry about that. I'm looking off of a sheet on my side here from where I already did the math. 00289. That's my new sagittal. That's my new sagittal depth over here. All right, so I'm going to add these two together. That gives me my 00489. What was the number we got before, right? So that's going to be 4.89 millimeters. All right, so this was for the first frame. So this is the answer for number 11. All right, and this is the answer for number 12. All right. Once again, the point I was trying to get by here, right? The power stays the same. The index of refraction, what it's made out of, stays the same. What it's in stays the same. The only difference is the diameter of the lens blank. All right, and so it's a smaller frame, so you would think it would also be a smaller blank. If it's a smaller blank, all right, and so the sagittal depth will then also be smaller, all right, which means that the center thickness is also going to be thinner, right? Because the center thickness is a combination of the edge thickness, which is a constant. The only thing different is the sagittal depth. All right, so you know that this number, the answer to 12, had to be less than the answer to 11. All right, there's the two numerical values, and there's all the math. Sorry about that mess up there. All right, but that is up to 12. So that's all the ones that have to do with using frame dimensions. The next two, oh my God, there's two more. The next two have to do with lens clock, and we'll come back for those. All right, we are back for the last two problems of this problem set, number 13 and number 14. And 13 and 14 have to do with something called a lens clock. All right, well, what is a lens clock? All right, well, clocks are used to tell time. What does time have to do with a lens? Absolutely nothing. All right, it's called a lens clock because if you look at a lens clock, it has a dial indicator on it, which kind of looks like the face of a dial, or it almost looks like a pocket watch, if you know what one of those things are. All right. What is euphemistically used called a lens clock is actually a micrometer. Okay, it measures a linear depth. All right, and so it actually has a protrusion out the bottom. Okay, and if you were to push in on this protrusion, it would move the dial indicator, the indicator on the face here. All right, and so I bring it in, I have a shorter depth, I bring it out, I have a longer depth. So it's giving me a linear measurement. All right, and so to do that, it's going to actually have two other protuberances on the outside here that are parallel to each other. All right, and so what I do is I take this thing and I put it onto the surface of, let's say, a lens. In this case, I'm talking in this one, this is a convex lens. It's pointing out towards it. And I now place the lens clock onto the surface of the lens itself. When that happens, it's going to take this and push it in. And when it pushes in, it's going to move in one direction this way. All right, now I'm going to read the lens clock. There's going to be numbers on the outside, and these numbers are going to correlate to dioptric powers. All right, the lens clock does not measure dioptric power. The lens clock is a micrometer. It measures linear distance. If you look at it here, what it's doing, if I bring this down such that that fellow there and that fellow there, that's this guy and this guy, are now stuck there, it's pushing this center guy forward. All right. What it's measuring is the difference between the edges here and here. This is what it's measuring here. It's measuring the sagittal depth. All right. So lens clocks measure the sagittal depth of a lens. Okay, that sagittal depth of the lens can be converted into a radius of curvature. That radius of curvature then can be converted into dioptric power. And that's what you're reading on the face here. You're reading dioptric power. I could also use the lens clock on a minus lens, something that has a concave surface. In that case, once I bring the two edges of the lens clock up to it, this thing is actually going to move out. In other words, the dial indicator will move in the opposite direction. So most lens clocks will read that way. They'll read, read plus on one side, they'll read minus on the other. Generally, the plus values are going to be in black, and the negative values are going to be in red. Okay, but there's many different manufacturers of lens clocks, so they all might subtle differences to it. But remember that a lens clock actually measures sagittal depth. And so the values that you're seeing on the outside are converted into dioptric values. All right. Well, what do I need to know how to figure out the sagittal depth? Well, the sagittal depth has to do with the diameter of the lens. All right. Square that times the power. Right. That's what it's trying to convert into. It's trying to convert sagittal depth into power. All right. Excuse me. And it's going to know twice what the lens is made out of and what the lens is in. Okay, and then once again, you're going to make that pretty much going to make the giant assumption. There's going to be many assumptions that people are going to make, and machines are going to make. And what the assumption is that this thing is in air. All right, and so all lens clocks, unless you're told otherwise, assume that you're actually measuring the lens in air, not in a bucket of water. That the lens itself, the power of the lens, is in air, not in a bucket of water, not in a bucket of oil. All right? But what you don't know, or what the lens clock doesn't know, what this thing doesn't know, is what is that thing made out of. All right? The diameter of the lens is kind of irrelevant at this point, because the diameter of the lens, no matter what it's made out of, the diameter would be constant, so that would be a constant. So I don't have to worry about that fellow there. All right? But I do need to know what it's made out of. So all lens clocks will be calibrated for some sort of indice of refraction of what that thing is made out of. Okay, and by rule of thumb, unless you otherwise, most lens clocks are calibrated for a value of 1.5. All right, and glass, basically. Or, so figure CR39, 1.498. That's pretty close. And then glass would be 1.5. Crown glass would be 1.53, let's say. So it's kind of in between. So that's where the 1.5 came from. And so they're not bad at estimating the power of a surface as long as you're correlating to what it's made out of. So for crown glass, for CR39 resin lens, that's great. But when you get up in the higher indice lenses, you're getting up in the 1.7s and 1.9s along those lines, the values that you're seeing on the front of this are not correct. You are either overestimating or actually underestimating the power of the lens, unless you're using a lens clock that is actually calibrated for that indice of refraction. All right. All right, so understand what the lens clock does. That's what a lens clock does. All right, now for problem number 13. It's telling you that a lens clock reads -5, all right, in all meridians on the back surface. All right, so I have a lens here that I have a -5 lens, so I know that the back surface has a negative curvature to it. And so if I take the lens clock, what am I going to use here to? Here, that's my lens clock right there. You go. And so I'm going to take the lens clock and I'm going to put it this way, and then I'm going to put it this way, and then I'm going to put it this way, and then I'm going to put it this way, and then I'm going to put it this way. Right? All meridians. I'm going all the way around. And they're telling you that in all meridians, all right, the value comes out to be a -5. All right, and so that tells you that the power of the back surface of that lens, that's what they told you there, the back surface of the lens has to be a -5 sphere, right? In all meridians, it reads 5. If that is the case, then it's a -5 sphere, all right? If it has an astigmatic surface to it, the powers are going to be different all the way around. You're going to find one maximum value, and you're going to find one minimum value, and all the other values are going to be somewhere in between. But in this case, the way the problem was written, it was -5 in all meridians on the back surface. So you know that the back surface is a -5 value. It reads +3 in the 150th meridian. And this is on the front surface now. And so on the front surface, it reads a +3 in the at width or in the 150th meridian. And it reads a +475 in the 160th meridian, or in the 60th meridian, not the 160th meridian. All right, so it has a minimum power of 3 along the 150th, and it has a maximum power of 475 along the 60th. You have now found, so the front surface is astigmatic. All right, the back surface is a negative value. This is the front surface here. All right. And so the excuse me. And so the front surface has a value. You can put that on an optical cross if you want to, right? So we got it here, we got it here. That is 60. That is $1.50 over here. This is a +3 over here, and this is a +475. This is the front surface. All right, this is the front surface. The back surface, by contrast, this is going to be the 90th. This is going to be the 180th, is a -5 sphere, which means it's -5 in both meridians. Okay. All right. So over here, this guy. All right. So we generally like to write in minus cylinder. So we could do it in a minus cylinder, right? That would be a +475. That's going to be its corresponding axis is the 60th, and to get from 475 to 3, I have to take away minus a 175. Right. And so that is the power of the front. That's over here, so that's a -475, -175. I'm sorry, a +475, -175, axis 60. All right, that's it. That's in minus cylinder form. You could also write that in plus cylinder form. Don't matter. But generally, they like stuff written in. The answers are going to be in minus cylinder form by convention. So we'll just do it that way. All right. So the front surface is astigmatic. All right. So this is an astigmatic front surface, and I have a spherical back surface. All right. What is the approximate power of the lens? All right. Well. What you can do is just take the power of the front, and so the power of the front plus the power of the back, and that should give me approximately the power of the total. All right, now that does not take into consideration any thickness of the lens, but for the purposes of the problem, you'll just add the two together. So I can take the 475, right? I can take the -175. And the axis 60, that's my front, and then I'm going to add to that my spherical -5. So that's it there. The sphere doesn't have any value there, so that's just a 0. And I'll just add those two together. And so this guy correlates. This guy just transfers down, excuse me. And then this, I'm going to take a +475. I'm going to take away 5 from it, and that's going to leave me with a quarter diopter. And so that's going to be the approximate power of the lens itself. All right. What is the approximate power of the lens? What is its base curve? Okay, its base curve is going to be, so this is the front base curve, and this is the back base curve. All right. And so when people talk about the base curve, they're talking about the front. All right. So if they're asking you what is the base curve, and it means that on this one, you're going to have your base curve is going to be this guy. All right, that's your base curve. All right. What's the other thing they're going to talk to you about? They're going to tell you it's going to be the steepest or the flattest. All right. And so one of the base curves is going to be a 475, and then the other one is going to be, I got to take $1.50 away from that. One of the other one's going to be a 3. And so those are your two possible front base curvatures. All right. To be honest with you, you can check in the answers which ones they want the base curvature to be. Because this is a, by the way, this is a, did I ask you? Yeah, this is a front toric lens. All right, this is not how ophthalmic lenses are made. In all dress ophthalmic lenses, what you're going to have is a base curvature on the front, which is going to be always positive and always spherical, and you're going to remove material from the back. So your astigmatic correction is always on the back. All right. In other words, it is a back toric lens. It's always the way it is. In this case, the way they gave you the problem, it's a front toric lens. All right. And so you were told in lecture which one of these two to choose for as your base curvature. Whichever one he told you, you'll go with. It's very academic to me. But in any case, that's how you go that way. So you have a spherical back surface and an astigmatic front surface, which is kind of odd. Was this lens made in plus cylinder or minus power? All right, well, you can only remove material from the back surface. All right, and so that's why we always deal with minus cylinder form. All right, if you have a toric surface on the front, the only way for you to manufacture that is to mold it in that place. In other words, you can't remove material; it has to be molded in, and so that you're adding plastic, and so that has to be plus cylinder form. All right, that's just a simplistic way of coming to that conclusion. Was the cylinder made in plus or minus cylinder form? That's plus cylinder form. What is the base curve? I would go with the steepest one. I go with 475, but once again, that might not correlate to what you're told in the lecture, so check the answers for that one. That's 13. All right, last one. All righty. And so this is going to be number 14. Number 14. All right, a lens clock reads 675 in the 75th meridian. What do we got here? So plus 675 in the 75th meridian at, with, or along the 75th. It's going to read 675 in the 160th. 675 at, with, or along the 165th. All right, well, if I take 75 and I add 90 to it, that comes out to be 165, which means that if I put that on the across, that is the 75th, and that is the 165th. That means I got 675 here, and that means I got... Wake up. Means I got 675 here, and I got 675 here. So I got 675 here, and I got 675 here. All right, and so that means that this is spherical. All right, so that tells you on the front surface. So I know that the front surface is a 675 sphere. Easy enough. All right, so on the back surface, however, it tells you that I have a minus 475 at, with, or along the 75th, and that I have a minus 3 at, with, or along the 165th. All right, I'm going to have to do the same thing. All right, so on this side, I have now over here, once again, this is for the, this was the front, and this is going to be the back. All right, so that's 75 over there, that's a 165 over here, and they're telling me that 75th, it's a minus 475, and over here it's a minus 3. All right, and so that's your optical cross now. And so I'll start out here because we want to put that in minus cylinder, right? That just tends the way we write stuff. 475 here. To get to here, I got to take away 175. Its corresponding axis was the 75th. And so this is for the back. All right. And then we're back to the same thing. What is the approximate power of the lens? Well, the power total, I can say, is equal to the power of the front plus the power of the back. All right, that's a lot. There's a lot of caveats that go along with that, but for the purposes of this, we'll just add the two together, just like you took two trial lenses and kind of stuck them together. We ignore the thicknesses and things along those lines, but just for the purposes of the problem, we'll do that. So the front is going to be a plus 675, and that's going to be a sphere, which means it's not going to have any powers that way. And then the back is the 475, the minus 175, and the axis 75. And so I get 675. I'm going to take 475 away from that. That's going to leave me with a plus 2. That's going to make total plus 2 minus 175, axis 75. That's going to be the approximate power of my lens. All right, what is the base curve? The base curve is now going to be the front base curvature. All right, and so I have a lens that looks like this, and that is a dress ophthalmic lens, which means I have a positive front base curvature and I have a negative back base curvature. And in this case, I really don't have a choice of front curvature. It's going to be that, and so the front base curvature is going to be the 675. All right, so that's going to be the base curve. All right, easy enough. And then, was this lens made in plus cylinder or minus cylinder form? Well, this was the negative surfaces on the back. All right, that's where the astigmatic, the spherical surface is on the front, the astigmatic surface is on the back. And so this was made just like a meniscus lens or a dress ophthalmic lens. So it started out with a blank that had a positive spherical base curvature, and material was removed from the back. And so that is in minus cylinder form. Right, that's the way lenses, the vast, actually all dress ophthalmic lenses are going to be made that way. All right, only there really are no dress ophthalmic lenses that are manufactured in plus cylinder form because they cannot be generated on any conventional machine. You can say that a progressive lens profile, which we'll talk about in the future, are molded into the front, and so that possibly could be conceived as a plus cylinder form on the front, but once again, the prescription is actually always grounded on the back, so that would still be minus cylinder form. But anyway, that is the simplistic answers to the question. So that is 13, 14. Wow, 14 problems. Now, some of these were, I believe, your weekend assignment, so if you need to know how you did on that, that's how you do those problems. Okay, and then once again, we can discuss this also in PSS. All right, so that's it. All right, see you on the next one.